I am a little jet lagged. I'm going to talk about trees, but apparently people are talking about different things here. How many of you have done gardening before? Okay. How many of you have written compilers before? Okay, so that actually everybody here have done work with trees. The ones who worked with compilers and the ones who worked with gardening. This is report or progress result of the summer of Haskell 2016, mentored by Simon. Simon is sitting here, and Jax Garrett, who's not here, and also I closely worked with Richard. He's here, and sorry for the photo. Is the talk being recorded, by the way?
Yes.
Yes. Okay. So Alan, sorry, that's the only photo I have from you from GitHub. And that's Nicholas Brewery from Chalmers. Okay, so also this thing happened because of the work inside the community. With Edward, I know Ryan, I know other authors were there, I don't remember their names, I'm sorry, and the whole community. But I just want to pick Edward out, and I want, if it's okay with you guys, I want to have a round of applause for Edward, that possibly maybe see this video, for organizing the Summer of Code. For this year. And well, I mean, I'm grateful to all of you for giving me this opportunity. Well, part of this share belongs to you guys. You paid for it, and thank you for this opportunity. So, well, we have GHC. In GHC, we have an ASD, we have a parser. We have a printer, and we have other things inside. We have Haskell Suite, or just Haskell source text packages. We have an ASD, we have a parser, we have a printer, and other functions defined. We have template Haskell. We have ASD, we have a parser, we have a printer, and other things for it. You are tired of hearing about these things? I did it intentionally, and you better be, because every person who worked on this thing has spent for each of those things months and months of code. Leonard is sitting here and worked on a renamer for one of those things before. Okay, and then I did also. I did my PhD on quoted domestic languages with Phil Wadler, my supervisor, Sam Lindley, and Joseph Spinelson from Chalmers. We wanted to use quotations to just produce code out of that, and then we had Haskell ASD would produce C for DSLs like feldspar that produces C code. We want to produce SQL for language integrated query systems, and we want to produce VHDL out of Lava. And you want to use quotations to do that. Great! So I have quotations, I get the ASD out of that, I know the template Haskell has this ASD, I can use it. Now I want to produce C code, and I need types. Oh! I need types. Okay, we have typed quotations. We have the top level type for them. I can somehow get a hold of that. But I don't have type of every single node in there that I want to produce C out of that. C is for compiling, you need types in C. Okay, and then I had to define my subset of ASD out of template Haskell. Write my own type inferencer for that one. Me also, and then a printer and dishugger and other functions. And then people came up to me and said, oh, why don't you add this extra feature? Oh, I have to write the whole GHC. And I didn't want to do that, and that isn't the same thing to do for your 3-year PhD in UK. Okay, and that's why I said enough. And then many people actually came to this point and said enough. Okay, and enough with this craziness. Let's hack up GHC and get the stuff inside it out. Let's get the ASD out, let's get the parser out, let's get the printer out, let's get the deshuggerer out, and the type inference engine, and etc. But there are problems, and I'm sure that you have heard about that one. Well, the main problem is that the trees that you have come in different flavors. Some of them are non-decorated, some of them are like template Haskell, non-decorated plain trees that we have. And the other ones are decorated and have all these things on top of it, right? And then each phase inside the compiler adds new decorations to these things, requires new information from these kind of trees. For example, type inference just stores the types that it infers and pass it to the next phase to just go ahead and process those things, right? So every phase inside the compiler adds new information to these trees for the processing of next phases, okay? And then each of those things, trees may be defined in different ways, okay? You may define a stuff, this is a very simple language. You might define a stuff in a plain way, like it looks like template Haskell, doesn't have any annotations. You might define stuff in a left way or right way that has all these annotations, these, you can see the mouse pointer in the end? Like type, like source locations, and etc. Okay, so you have two ways of defining these things, and they both are needed and helpful, right? These bits. And look at this. If you just focus on this one, we have two sorts of decorations here. Some of them are new constructors, like that out. People who work on HSC have seen this out prefix constructors that rename and other things produces. And then, and also you have to add new fields. So you have to have this this direction of the extension that you need to introduce new constructors. You have also the other direction you have to introduce new fields. So you need both direction of extensibility here. Okay. So we call to the one that adds a new constructor as column extensibility, and the one that adds new fields as row extensibility. The name doesn't matter. The fact is that you need this both direction of extensibility in GHC at least. Okay? And there are two ways, common practice, to just deal with this problem now. Maybe there are smarter solutions. I'm saying common practice here, smartly. Either we use this big decorated tree, the one on the right, everywhere, and that comes with its own problems, or we have 3 different ASDs per each decoration annotations that we need. Okay? So the first one, the upper one that you use the same big large ASD, have the issue that it has unnecessary information inside it and unnecessary dependencies. Okay, if you want to use the GHC ASD, you have to depend on the whole compiler, or at least big part of it. But there are no duplications, right? Because you have one ASD here. And if you want to use the other technique, you have to. You don't have unnecessary information, but you have duplication. You have 3 trees here. Okay. So we talked about this problem a little bit, like a month or so, to solve this problem. And our approach, the solution that we came up with, is to just declare ASDs using extensible data types. Whoa, I'm going to explain what that means. And then define decorations, this information added to that one, as extensions. So we can extend our trees as we go. Okay? So what does it mean? That we have a base X extensible declarations, that I can extend it both to unannotated one and the annotated one. Both the decorated one and the non-decorated one and the decorated one. Okay? Okay, so basically the same, that's like the lower approach that I showed you before, that you have 3 different ASDs, but this time all those 3 ASDs are extensions of the same base extensible ASD. Okay? So what is that? Now that the question, the big question, the big challenge is, how do we declare this extensible data type, or in general, how do we declare extensible data types where GSC does not support them as an off-the-shelf feature, right? But I want to show that GHC, thanks to this type system, is rich enough that we can encode these things right inside GHC without any language extensions. Okay, we can introduce syntax to make it convenient, but GHC already supports these things. Okay, so the naive encoding that I want to talk about, the simplest one, is to just add a type variable per each place that you may extend. And those things stand for new extensions. Each constructor is going to get a new variable that's going to stand for new fields added to that. And the whole data type is going to have a new constructor with a type parameter that stands for new constructor to the data type. This is a naive way to do that, right? And you can see lots of type parameters there. A smarter way, well, I mean, you can of course show that both of those trees that I showed in the beginning is instances of that one, right? By just setting those parameters. Okay, that's one of them, and this is the other one. Okay, and I use pattern synonyms here to declare these new constructors. Okay, but this is a big, large thing. You don't want to do that in practice, right? So you can make it more compact encoding. Instead of writing the one on the top, you want to write something on the bottom. Instead of having multiple parameters, you have one single parameter. We call it extension parameter, and we project out of that. Here we're using a unique label to project and to label each of these holes and project out of that thing. Here in this case, I am using symbols, sub-level symbols. We can use other kind of labels and indications that here, I want to have extension for var x, I want to have extension for abs x in that location. Okay? But the key thing is that that symbol should be somehow extensible as well. Okay? And but the main thing is, if you look at x is a higher order thing. There are variations. Where's Yavor sitting here? There are other kind of approach to encode these things that you can use the functionalized version of that. And the reason to do this thing is because GHC does not have first-class functions that can be passed around partially applied. Okay, we can have a defunctionalized approach that uses this approach that you have this application thing here. Okay. So I have an app constructor at the type level, gets this X, and passes this one these symbols. What does it imply? Means before, when you were writing this thing to set every single of those big list of parameters, now you are defining a type family to set out those parameters. Okay? Good. We could make the stuff more compact. I mean, same applies for the decorated one. But pattern synonyms are the same thing as before. Okay? But we can go even further. We can try to do existentials. If you have a data type that has existentials inside, we can do the same thing with them as well. So what do I mean by that? If I have the one on the top, that's on the last constructor add, it has A and B that are existentially quantified. I can just, and then I want something that A and B is used for extension, the one A pair being down there. I can still come up with an integral following the same philosophy to just do that one. And here is how I do that. I have this ASD. There is typo. These things are all going to have an X here, but that's a side thing. I'm going to have a kind level data type, a type level data type, but I'm going to pass these existential types to it. Okay? And then I can define an instance like this. I can say, well, I mean, this is the extended one, but I can say, hey, in the location of @t, when I have type parameters A and B, the extension is going to be this. Okay? So here you can just go on to existentials, and then even you can go further to full GADTs. I'm going to show that example to you. It's a simple expression language. Let me see. So fonts. Is the font okay in the back? Can you see it? Yes? Yes, okay. You want to write a stuff in a normal way, untyped way, and you want this expression language to be typed like this. Okay, I follow the same technique as before. I just add this extension parameter. I just use the functions version of that to apply it to these tags that I define. Existentials are passed to this tag, so I can later on use them. And then I can introduce. I use data family in this example instead of type family. And I can introduce these local type constraints as well, because I have access to that A and B there. Okay? And the good thing about that one is that I can define these typed evaluators. Okay, they are not tagged when I'm defining them. Okay. So you can see. Well, I mean, if I go back to my slides, if you have a list, if you are given a list of something or set of something, you know the definition of extension for that. You add an element to that list. If you're given two lists, again, you know the definition of extensions. You have two forms of extension, extending the first one or extending the second one, right? Or both of them, but you have two directions of extensions, okay? An ADT syntactically is composed of two lists, which one of them is a list of, a set of lists. So the first list is going to be the set of, the first set is going to be a set of the type arguments to the type. So you can extend that one. So syntactically, when you define an ADT, you can extend that one by having a new one. When you syntactically add new type variables to that. When you have a set of constructors, and then each of them are going to have a list of fields, then again you have two forms of extensions to that, either adding new fields or adding new constructors. So in total, ADT can be extended syntactically here in three ways at ADT declaration. Adding new type variables that we can support, adding new constructors that we can support, as I showed, adding new fields that we can support. For GADTs, we have two extra forms. Adding new local type variables, existentials, or adding local type constraints. That again, I showed an example to that. So, based on this simple notion of extensions to declarations, this encoding is complete syntactically for separate extensions. This is the power of GHC, that we can do this kind of extensions. Okay? And then, but you have heard the Vortex Nation, haven't you? At least 5 times, there were 5 talks in this event since Monday, or even on Sunday, about this different notion of extensibility. There is there's a design choice here that we have to make. Here, what we are doing is a more nominal approach. We are not competing, we are not doing any overlapping things with row polymorphism, variance, extensible variance, and stuff like this. We are declaring types. So extended data type B is going to have constructors that are referring to B, not something that at the type level you have sets of constructors and their types. Or just a type variable A with a quantification of this one has that field and doesn't have that field, and things like that. This is a very simple approach, and follows a nominal approach to do this kind of extensions. Okay? And as I talked about the fact that it was important to us to have both row and columns, add new fields and add new constructors. At least GHC needs that thing. It has these out constructors and has new fields of source locations and types and other things. Usually these approaches try to focus on one direction. For example, expression problem is about adding new, is about column extensibility, adding new constructors. Okay, there are valid concerns. This is different approach. Well, I mean, we do solve the expression problem here. We can add constructors, but we will focus on reusing data type declarations rather than how to define functions over these things compositionally and compose them together. Okay, that would be really nice to see generic programming over these things as well. Okay, and well, I mean, we are doing everything within Haskell now using the extension that exists inside GHC. Okay. Well, I mean, I started with this thing that I want to split up GHC. Well, that's a bad karma, being that's my first project. But now we have an encoding of extensible HSC and ASD, this surface ASD of Haskell. We have a separate parser. We just got inside GHC and could extract the parser out of that. This is on Git, and we have looked at different ways to do that. The process of doing the first two things was really cumbersome thing and mechanical thing. We have sets of tools and sets of machineries. I have a template Haskell thing that basically you can generate these things automatically. So part of that. Okay. So next steps. First of all, we are claiming that we are gonna get this ADTA inside Haskell, this beautiful HSC, and we're gonna make it into 2 parts. When you just make a stuff split in 2 parts, the natural question is the composition is going to perform as well as the original one? So we have to do some performance test here. Well, I mean, the key idea right in the beginning is that we want to be able to just split a GHC into different packages and give it to users. And this is also a community work. I cannot do it by myself. This will break code of every single one of you guys who work on GHC. And we need to talk about these things. Okay? How to split GHC into packages. I did for parser, but I know that if I want to commit something like that, it's going to break the whole system. And I don't know how to do that with having a good, clean Git commit there. So I have a good, clean history so you guys can review that I haven't screwed up somewhere. Okay? The next step is going to be, well, I mean, we said we have 3 ASTs. We have Haskell source X, we have template Haskell, we have this AST inside GHC. Next question is, can we replace template Haskell by that? Every single slide when I was sitting here had the word template Haskell in them at least once. Okay? If I'm going to replace that AST, I'm going to break something. So people have solutions. We have talked with Anders about that and others. And we have to talk about those things as well. Okay? Well, I mean, the next thing can be interesting. David Christiansen, where are you? You have heard about his talks, and what these guys do in Idris is really, really cool. They can resurface what they have inside the compiler, the machinery, and they can provide to the users and people who write method programs. They can do proof automation using those things. The focus of that work was to just resurface this elaboration process inside the language. We can resurface, we can elaborate other parts of the compiler as well. So that can be something interesting to look at. I am interested to work on that one for my PhD work. Well, I mean, and the next obvious question that everybody asks is, can we have this one as a language feature? Yes, we can, but there are some practical things to consider. We have to assess so many of these details. Okay? Yes, that's my talk. Thank you for giving me this opportunity once again, and thank you for listening to me. Thank you.
There's time for a few quick questions in the back.
So, when you're defining an inductive data type, you open the induction, and that works really nicely with normal Haskell, as long as you have just one data type instead of mutually inductive.
So,
does this technique apply when you take points of something where some parts of it are mutually inductive?
I guess I have to repeat the question, and it would help me to see if I understand you correctly. You're asking, does this thing scale to mutual recursion in types? And the answer is yes. Specifically, one of the main concerns we had, immediately when you're going to work on these things, you have patterns, and then you have expressions, and you have view patterns that have expressions inside them, and you have these mutual recursive definitions. Yes, it scales. That was one of our original concerns there. So we do support mutual recursion.
Right, but I mean, does it work if you want to use this in this exact thing that you just said, expression patterns, whatever, and if you also want to keep the recursion or induction open?
Sorry, keep the recursion what?
Open.
Keep the, yeah, you can. Yeah, if you want to, we can show you some code after this, okay? Good question.
Any more?
Any more good questions?
We've run out of time anyway, so let's thank the speaker again.